Okay, so what we need right now is something that will allow us to compare objects. So we're going to talk about binary relations, but we can extend this to n-ary relations where we compare n objects. The difference is really superficial. We're just extending it to more sets. So we're going to need two sets. So let S and T be sets. Now a relation R from S to T is a subset. It is a subset of S cross T. So the Cartesian product S cross T. I remember the first time I encountered this definition, the notion of relations, I thought, this is absurd. We're basically coming up with a new word which behaves essentially exactly like a Cartesian product. Why are we adding some vocabulary when we could just use Cartesian products to talk about relations? Well, it becomes very useful to consider relations as a separate object than Cartesian products because we treat them differently. So for Cartesian products, we really consider them to be points. The objects of interest are points. Okay, so pairs x, y, for instance. But in terms of relations, I'm not so much thinking about points. I'm thinking about how x is related to y by my relation R. Okay, so this is the notation that we'll be using for relations. Now, as usual, using examples, we're going to see the real value of talking about relations. So the trivial examples are the empty set and the entire set itself, okay? And those are some really boring relations because in the first case, the empty set, nothing is related, okay? No objects are related between each other. And in the second case, where we have the entire set, well, it's also just as boring because we have everything is related to everything. Trivial cases are often useful when you're looking for some counterexamples. Anyways, for something more interesting, let's talk about capital Pi to be the set of points in a plane. Let capital delta be the set of lines in the same plane. So what we're going to do is define a relation capital I, so it is a subset of the product of all my points and all my lines. And what we're going to define here is incidence. So I here is equal to the set of pairs x and capital D. So x is a point and D is a line. Actually, I should have used a capital L here. And x, I'm talking about all the points such that x lies on that line, okay? So this allows me to say that x is incident to a line L. What this refers to is if a point is incident to a line, well, it lies on that line, okay? So that is how some points are related to lines. We have incidents. Some of the more most commonly used relations are inequalities. So we can define inequalities as relations. So we're going to define the inequality on the integers. You could switch that for real numbers or rational numbers if you'd like. And what I mean by a relation on the set of integers, I simply mean that I'm taking both of the sets. It's a subset of the Cartesian product of two equal sets. Okay, so my strict inequality consists of all pairs xy that are in the set of integers, both in the set of integers, and we're going to take y minus x, and we want this to be in the set of natural numbers, or you could say the set of positive integers. And similarly, actually in this case, we would omit 0 because it's a strict inequality. When we were talking about the partial order, where it's smaller or equal than, what we're talking about is the product where the same subtraction is in the set of natural numbers. Okay, and you'll see that this works. 3 is smaller than 4, and that is because 4 minus 3 is equal to 1, and that is in the set of natural numbers omitting 0. And 3 is not smaller than 3, and that is because, well, 3 minus 3 is equal to 0, and that is not in the set of natural numbers omitting 0. Okay, so remember how we defined this? We defined a relation R to be a subset of a Cartesian product, and really what I want you to internalize is that when you're visualizing Cartesian products, you're talking about pairs, and when we're talking about relations, we're really, trying to compare elements.